Here's a scenario you've probably seen. You deploy your node.js app, run it as the Ubuntu user, and it tries to write a log file to /var/log/myapp. It crashes immediately with permission denied. Or you install an SSL certificate as root, and then your node.js process running as Ubuntu can't read the private key. Or you upload a deployment script and try to run it, but the shell says permission denied even though the file is right there. All of these situations have the same root cause, Linux permissions. And until you understand how they work, these errors feel completely random. Linux permissions are the operating system's enforcement mechanism for the principle of least privilege, the security principle that says every process should have access to exactly what it needs and nothing more. Your web application doesn't need to read /etc/shadow. Your node.js process doesn't need to write to /boot. And root shouldn't be running your application, because if your app gets compromised, the attacker gets root. Permissions are how Linux enforces these boundaries. They're not bureaucratic obstacles, they're the security model that has kept Unix-like systems secure for 50 years. Once you understand the model, the errors become informative rather than mysterious. Every file and directory in Linux has exactly 3 identity categories associated with it: the owner, the group, and everyone else, which is traditionally called world or other. The owner is a single user, typically the user who created the file. Your app files are owned by Ubuntu because Ubuntu ran git clone. /etc/jinx/jinx.conf is owned by root because root installed Nginx. The group is a named set of users. Groups exist so that multiple users can share access to files without making those files accessible to everyone. For example, if you have a team of web developers, you might add them all to a web dev group and give that group read access to your app files. World or other means everyone else. Any user on the system who isn't the owner and isn't in the files group falls into this category. Here's what this means practically: when a process tries to access a file, Linux checks 3 questions in order. First, is this process running as the file's owner? If yes, apply owner permissions. Second, is the process's primary group the files group? If yes, apply group permissions. Third, apply world permissions. Linux stops at the first match, it doesn't combine permissions. This is the entire permission model. 3 identities, 3 sets of permissions. Once you grasp this, chmod and chown become mechanical. Run ls-la in any directory and you'll see output like this: rwxr-xr-x1 Ubuntu 4096 June 5th server.js. That first column rwxr-xr-x is the permission string. Let's decode it character by character. The first character tells you the file type. A dash means a regular file. The letter D means a directory. L means a symbolic link. B or C mean device files. The remaining 9 characters are 3 groups of 3. The first 3, rwx, are the owner's permissions. The middle 3, rx, are the group's permissions. The last 3, rx, are the world's permissions. Within each group of 3, the positions mean r equals read permission, w equals write permission, x equals execute permission. A dash in any position means that permission is denied. So rwx means read, write, and execute are all allowed. Rx means read and execute are allowed but write is not. R means only read is allowed. Means no access at all. For your server.js file with rwxr-xr-x, the owner, Ubuntu, can read, write, and execute. The group, Ubuntu, can read and execute but not write. Everyone else can read and execute but not write. This is a typical executable script permission. Chmod is how you change file permissions. It stands for change mode. There are 2 ways to use it: symbolic mode and octal mode. Symbolic mode uses letters to describe what you're adding or removing. Chmod plus x script.sh adds execute permission for everyone. Chmod u plus w server.js adds write permission for the owner, u equals user/owner. Chmod go w config.json removes write permission from group and world, g equals group, o equals other/world. Chmod a plus a readme.md adds read for all, a equals all. Octal mode uses a 3-digit number where each digit represents one identity's permissions as a sum: read equals 4, write equals 2, execute equals 1. Add them up for the permissions you want. Chmod 755 script.sh means owner gets 7, 4 plus 2 plus 1 equals rwx, group gets 5, 4 plus 1 equals rx, world gets 5, rx. This is the standard permission for an executable that everyone should be able to run but only the owner can modify. Chmod 644 config.js means owner gets 6, 4 plus 2 equals rw, group gets 4, r, world gets 4, r. Standard for a config or data file only the owner can write, everyone can read. Chmod 600 private.key means owner gets 6, RW, group gets 0, world gets 0. This is what SSH and SSL certificates require, readable only by their owner, completely hidden from everyone else. The pattern to memorize: 755 for executables and directories, 644 for regular files, 600 for private keys and secrets. While chmod changes permissions, what can be done? Chown changes ownership, who the file belongs to. Chown stands for change owner. Chown Ubuntu Ubuntu/home/Ubuntu/myapp changes the owner and group of the myapp directory to the Ubuntu user in Ubuntu group. This is the format: chown owner or group path. Chown Ubuntu/var/log/myapp.log changes just the owner, the group stays the same. Chown or Ubuntu Ubuntu/home/Ubuntu/myapp applies the ownership change recursively to the directory and everything inside it. The R flag means recursive, it descends into subdirectories. Why does this matter? Here's a common production scenario: you deploy your app as root, which means all your files end up owned by root. Then PM2 tries to read them as the Ubuntu user. Permission denied, because Ubuntu doesn't own the files and the world permissions don't include read access. The fix: sudo chown or Ubuntu Ubuntu/home/Ubuntu/myapp. Now Ubuntu owns everything and can read it freely. Another common scenario: certbot installs your SSL certificates as root into /etc/let's encrypt/live/. Your node.js app, running as Ubuntu, needs to read the private key. You have two options: change the certificate's ownership to Ubuntu, not recommended for security, or use Nginx to handle SSL termination. Much better, Nginx runs as root to bind port 443, then proxies to your node.js app. Here's a permission concept that trips up a lot of people. The execute bit on directories doesn't mean run the directory as a program. On directories, the execute bit controls whether you can enter the directory and access its contents. This is crucial to understand. If a directory has execute permission, the X bit, you can cd into it and access files inside it. If a directory does not have execute permission, you cannot navigate into it or access any of its files, even if those files themselves have read permission for everyone. A directory with R permission, read but no execute, is a strange situation. You can list the files inside, because read permission allows listing, but you can't actually access any of them. You can see the menu but can't order anything. A directory with X permission, execute but no read, you can navigate into it and access files inside if you know their names, but you can't list what's there. You know the house exists and can enter it, but you can't see inside without already knowing the layout. In practice, you'll almost always want directories to have 755, rwxr-xr-x, owner can do everything, group and world can read and traverse. If you want a private directory that only the owner can access, use 700, rwx. The execute bit on directories is what makes them traversable. Beyond the basic read-write execute bits, Linux has three special permission bits that you'll encounter in production: setchud, and the sticky bit. Setchud, written as S in the owner's execute position, causes a program to run with the privileges of its owner, not the user who runs it. The classic example is the password command. Even though a regular user runs it to change their password, it needs to write to /etc/shadow, which is owned by root. Because password has the setchud bit and is owned by root, it briefly runs as root to make the write. You can identify setchud programs with LSL, they show RWS instead of RWX. Setchud S in the group's execute position has a similar effect but for groups. On files, it causes the program to run with the files group. On directories, it causes newly created files inside that directory to inherit the directories group rather than the creator's primary group. Very useful for shared project directories. The sticky bit, shown as T in the world execute position on a directory, means that users can only delete files they own, even if they have write permission on the directory. The classic example is /tmp, everyone can write files there, but you can only delete your own files. The sticky bit prevents users from deleting each other's temporary files. These bits are less commonly used in day-to-day work but important to recognize when you see them in ls output. Let's walk through the most common permission errors you'll hit in server deployment and exactly how to fix each one. Error 1: Ichis, permission denied when your node.js app tries to read its own config file. Diagnosis: ls-la to check the file's owner and permissions. Fix: chown Ubuntu config.json if it's owned by root, or chmod 644 config.json if the permissions are too restrictive. Error 2: permission denied when trying to run a shell script. You can see the file. You know it's there. But /deploy.sh fails. Diagnosis: LSL shows RWRR, the execute bit is missing. Fix: chmod +x deploy.sh. Error 3: Nginx gives a permission denied error reading a static file. Nginx runs as the www data user. If your static files are owned by Ubuntu with mode 700, rwx, www data can't read them. Fix, chmod 755 on the directory, chmod 644 on the files. Error 4, PM2 can't write its log files. PM2 runs as Ubuntu and tries to write to /var/log/pm2/ which is owned by root. Fix, sudo chown or ubuntu /var/log/pm2, or configure PM2 to write logs to your home directory instead. The diagnostic workflow is always the same: check what user the process runs as, check the file's owner and permissions with lslaw, and adjust with chown or chmod to align them. When you create a new file, what permissions does it get by default? The answer is controlled by a value called the umask. The umask is a mask that's subtracted from the maximum permissions to determine the defaults. The maximum permissions for a new file are 666, rwrwrw, readable and writable by everyone but not executable. The maximum for a new directory are 777, rwxr-xr-x. The default umask on most Linux systems is 022. When you subtract 022 from 666, you get 644. When you subtract 022 from 777, you get 755. So by default, new files are created with 644, rwrr, and new directories with 755, rwxr-xr-x. This is why you can read files created by another user but can't write to them. It's by design. Run umask with no arguments to see your current umask. You can change it with umask 027, this gives more restrictive defaults. Files get 640, rwr, and directories get 750, rwxr-x. This means group members can read your files but world gets no access at all. For production deployments, the default umask of 022 is usually appropriate. Your app files end up as 644 and directories as 755, which is exactly what you want. The umask is set in your shell profile files. If you want a non-default umask for your deployment user, add umask 027 to /home/ubuntu/.bashrc. One concrete question to lock in your permissions knowledge. Your Node.js app's private SSL key is owned by root with permissions 600 RW, meaning only root can read it. Your app runs as the Ubuntu user. Which is the most secure fix? Option A, chmod 644/etc/ssl/private.key. This makes the key world readable. Never do this. Private keys must remain private. Option B, chmod 777/etc/ssl/private.key. This makes the key readable by absolutely everyone. Catastrophically wrong for a private key. Option C, use Jinx to handle SSL termination. Jinx can run with the privileges needed to read the key, decrypt TLS, and proxy requests to your Node.js app on a non-privileged port like 3000. Your app never needs to touch the key directly. This is the correct answer, and it's also the standard architecture for production deployments. Option D, run Node.js as root so it can read root-owned files. This is the worst option. If your app has any vulnerability, an attacker gets a root shell. The answer is C, Jinx handles TLS. This is why the reverse proxy architecture isn't just about port mapping, it also provides a security boundary. Jinx runs as a more privileged process for the narrow purpose of TLS termination, while your application code runs as a less privileged user, limiting the blast radius of any security vulnerabilities. Next chapter, processes, PS, kill, and what's actually running on your server.